Welcome to this explainer. Today, we're diving into a really exciting conference presentation by researchers Dariya Dosi, Yash Kodam, and Arihant Jain from IIT Gandhinagar. They've just unveiled a methodology that's basically going to rewrite the rulebook on how electric vertical takeoff and landing, or eVTOL aircraft, plan their flight paths. Let's get right into it.
So, here's the absolute biggest bottleneck in the industry right now. How exactly do we maximize eVTOL operational range without just slapping a bigger battery on it? You know the drill. Batteries are heavy. Adding more capacity adds more weight, and you're instantly stuck in this frustrating diminishing returns loop. Well, these researchers decided to bypass the battery chemistry altogether. Instead, they're tackling the problem with radically smarter flight planning.
Here's our roadmap for this explainer. First, the eVTOL range challenge. 2, their unified trajectory optimization approach. 3, modeling aerodynamics and energy. 4, wind-aware flight strategies. 5, simulation and performance gains. And finally, 6, applications and future work.
All right, Section 1, the eVTOL range challenge, breaking past physical battery limits. Let's look at where we actually stand today. Your typical multi-rotor drone is limited to an operational range of, maybe 6 to 7 kilometers? That is barely enough to cross a small city, and even your fixed-wing VTOLs are capping out at around 10 to 12 kilometers. If we're ever going to see truly widespread autonomous logistics, drone delivery, or real-time emergency response, we literally have to break past these physical barriers. Traditionally, mission planners treat a flight like a rigid checklist. They chop the journey up into very discrete phases. You climb, then you cruise, then you descend. But doing it this way, one disconnected step at a time, creates these really suboptimal, choppy step profiles. So the IIT Gandhinagar team completely flipped the script. Instead of a checklist, they built a unified framework. They're treating the entire mission as one continuous time, coupled optimization problem. It literally looks at the whole picture all at once.
Moving on to Section 2, unified trajectory optimization approach. A continuous time optimal control problem.
Okay, so how does this actually work? The researchers engineered this comprehensive ecosystem that feeds a multi-rotor model and an atmospheric model straight into a highly sophisticated solver. And they're doing this using Kazadi. If you're not familiar, it's this incredibly efficient mathematical framework in Python designed specifically to compute complex derivatives. It handles the crazy nonlinear optimization effortlessly, which is a massive upgrade from traditional tools that honestly just choke on the unpredictable physics of multi-rotor systems.
By framing this whole thing as an optimal control problem, the system essentially performs this beautiful real-time balancing act. It is simultaneously optimizing horizontal velocity, vertical velocity, thrust, and altitude. They use a direct shooting method and advanced nonlinear programming, specifically the Interior Point Optimizer, or IPOT. This solver naturally navigates all those complex boundaries to just organically discover the most efficient path from start to finish, totally bypassing the need for predefined rigid waypoints.
Section 3, modeling aerodynamics and energy, dissecting the physics of the 3 degrees of freedom model. Now let's look at the physics, specifically the downforce, or negative lift, generated during forward flight. When a multi-rotor tilts forward to fly fast, the body of the drone acts almost like an upside-down wing, literally pushing the aircraft down. It creates a massive energy penalty because the motors are suddenly working overtime just to maintain altitude. Crazy enough, conventional point mass models usually completely ignore this. But by actively modeling this aerodynamic drag, this new framework accurately penalizes those super inefficient high-speed attitudes. And it's not just the physical shape of the drone. The environment plays a huge role too. Experimental data from the team proves that motor and propeller efficiency is highly sensitive to air density, which, as we know, fluctuates wildly with temperature and altitude. So they baked these real-world, regression-based efficiency maps straight into the model. That means the solver knows exactly how atmospheric factors are going to eat into its battery budget. All of that incredibly complex physics gets distilled down into a closed-form power consumption model. In plain English, the exact electrical power drawn at any given second is dynamically calculated by adding the aerodynamic propulsive power requirements to the power needed for climbing. It is insanely precise, guaranteeing the software never, ever asks the drone to pull a maneuver the battery can't physically handle.
Let's jump to Section 4, wind-aware flight strategies, exploiting atmospheric gradients. To make this strategy truly wind-aware, they integrated a stochastic or predictably variable wind speed model. Because wind behavior shifts dramatically depending on altitude, this model basically gives the solver the ability to soar. Without being spoon-fed any predefined waypoints, the system autonomously hunts down the absolute most energy-efficient cruise altitudes just to catch favorable winds. It's brilliant.
But obviously, you can't just let the math run wild into physically impossible scenarios, right? The solver is kept in check by strict real-world operational constraints. Cruise speeds are hard-capped between 5 and 25 meters per second, vertical speeds are safely bounded between -3 and 5, and the operating altitude stays within valid airspace limits of 50 to 4,000 meters. And most crucially, it enforces strict usable battery capacity limits. So every optimized flight it spits out is actually 100% feasible in reality.
All right, Section 5, Simulation and Performance Gains, validating the optimal trajectories. Let's look at the actual numbers.
28. That is the magic number here. By totally abandoning that old climb, cruise, descend checklist and unifying everything into a single, continuous optimal control problem, the simulations showed a massive 28% increase in operational range. I mean, think about that. Unlocking nearly a third more distance from the exact same physical battery, that is an absolute game changer. And when you put the unified, optimized path side by side with conventional, real-world drone traces, the difference is night and day. The optimizer generates these beautifully smooth, dynamically feasible velocity curves. There are zero sudden, jagged spikes in thrust. Not only does this save a ton of battery life, but it also puts way less wear and tear on the physical hardware. You can really see this autonomous soaring in action on return missions. If you follow the projected altitude profiles, take a look at the simulation line here, you'll notice the solver strategically climbs high on the outbound trip to ride a strong tailwind. But then, on the return journey, instead of fighting that exact same wind, it autonomously decides to fly low to the ground to dodge the headwind. It computes this entire environmentally aware strategy totally on its own. Finally, Section 6, Applications and Future Work. The path forward for autonomous logistics. So, where do they go from here? The researchers' next big step is to translate these amazing software simulations into hardware-validated reality. They're gearing up for hardware-in-the-loop experiments and planning to expand the wind models with even richer experimental atmospheric data. Basically, they want to make absolutely sure these theoretical gains hold their ground against the completely chaotic nature of real-world weather. So I'll leave you with this thought. If we can instantly unlock 28% more range from our existing drone fleets, literally just by updating their software, how is this going to completely redefine beyond visual line-of-sight logistics? Imagine the impact on emergency response times, medical deliveries, or industrial surveying when your drones can suddenly fly nearly a third further than they could yesterday. It's huge. Thanks for tuning in to this explainer.